Now you're recording, so that would have been another fun one, just not record the damn thing at all.
You didn't need to catch that first part anyways.
Yeah, that's what was important. That's just for the people who actually show up in class, the special people. Okay. So, anyway, today we're going to talk about string. Strings. First of all, I'm going to mention that the data we're going to use for today, which contains a lot of string information we're going to work with, is actual King County food safety data I got from data.kingcounty.gov. This is a really big data set. If you want to load these data and work with them, save them. Do not continually load them by doing read CSV directly on here because it's like a 100 meg file, so you'd be re-downloading that every time. If you work with these in a script or something, these are the ones we'll use for the mapping homework next week. Download them locally, load them locally, something like that. But yeah, we're just going to use food safety inspection data for Seattle, which is fun because it means for the next 2 weeks we're going to explore what places in Seattle will poison you if you eat there. Very fun. Yeah. I'll give you some hints. They're all next to this campus. Yeah. Okay. Anyway, so we're going to be talking about strings today. So the term string is a sort of general programming term that refers to any sequence of characters. So not a single number or something, but a sequence of characters. The most common strings in the world of computing and programming are strings of binary. Things like, a series of zeros and ones. And these ones you'll see, this is a string of a given length, a space, another one here. This entire thing could be a single string, or each of these individual ones could be considered a string. So binary is usually used to represent any form of information at the lowest possible level. Like there's no way of storing information essentially below on and off or true and false. So these strings like this are just logical data in string format. But any type of character data, anything that is not a single number, but is a series of things in R, is character data or strings. So things like words can be strings, entire paragraphs can be a single string or a series of strings. You could have a single element of a object in R be an entire book, and that could be a single string. You could divide that up into multiple strings where each string is a page or a paragraph of it or something like that. But what it comes down to is that it's a series of characters. Those characters could be numbers, but they're differentiated from a single number in that they're not treated as being something that's just a number. Like, we don't look at this and say that this is, it wouldn't make any sense with a leading zero, but we wouldn't look at this and say that this is, 1,110,000. It's that's 0,111,0000. Right? So they're sequences of numbers rather than a single number, thus it's a string. So, basic string stuff. We've seen before that there's a function nchar that will get the number of characters in a string that you give it. So we'll take a vector or a single string, and it will tell you how many characters there are in whatever strings you feed to it. So using these data, we could extract the zip codes from these data and be like, okay, let's see how long our zip codes are, because normally a zip code should be 5 digits long. In this particular data set, 258,629 of these are 5 digits, and then inexplicably exactly one piece of data in here has a 10-digit zip code, right? So nCharacter will tell us how many digits or something are in it. So in this case, zip code are something that you could look at and be like, that's a number. But in reality, zip codes don't have there isn't a real meaning between going from 97439 to 97440. There's no order to these things. Zip codes, ID codes for individuals, things like that in data should be treated as strings rather than treated as numeric. Store them as strings so you don't accidentally do mathematical manipulations on them. Anyway, nCharacter will let you look at what is the length of a given string. There's a function substring, which you might be familiar with from the voting homework. It was used in some examples in class as well. Substring is used to extract a substring from a particular string. That being, extract a smaller string from a larger string. So say we only wanted to get the first 5 digits of those zip codes. Say we had a lot of 10-digit zip codes we weren't interested in. We were only interested in those first 5 digits to them. We could use substring to extract those first 5 digits like this. So I'm taking the restaurant's data, piping it to a mutate, and saying this new variable zip5, which is going to be 5-digit zip codes, is going to be equal to the substring of the zip code variable starting at the first character, ending at the 5th character. So characters 1 through 5 of this, and that's just going to give you 5-digit zip codes. So substring extracts substrings. You could, for instance, let's say you were only interested in, let's say they were all 10-digit ones and you only wanted the last 5 digits. You could say substring zip code start at 6 and end at 10, and that would extract places 6 through 10 and give you the last 5 digits. You could also extract stuff in the middle. If they were 10 digits long and you only wanted the middle 4 digits, you could start a ways in and finish before the end of it. You can do whatever you want with substring.
Is this using the stringer?
Not yet.
Okay.
So substring is the base R version of a stringer function that I'm going to get to in a minute, because we're going to focus on using stringer here today. But want to know that for everything you can do in a package like stringer, there's a base R equivalent. Okay. Paste we've used a lot in this class. Let's say what we want to do is, with all these data, we have columns for things like we have their street address, the city they're in, the zip code. Let's say we want to produce a full mailing address for everything in this data set. We could do something like this. We take our restaurants data, we're going to create a new variable called mailing address, and for that we're just going to paste together the address variable, comma, space, the city, comma, space, Washington, the 5-digit zip code, and we're going to have no separator between them because I've put the spaces inside these already. If we do that, all of these get put together into full street addresses, like 10 Mercer Street, Seattle, Washington, 98109. Right? Let's say you have a whole database of individuals that you're doing repeated surveys on, and you want to be able to pump out a quick list to Excel to send to, say, mailing services on campus. This is actually how I've done that in the past to get mailing addresses to send out surveys. Say they were all in individual columns or something like that. Paste them together, put it out in the format that you want. Paste. So, there's a option you can use on paste that, unfortunately the person who used it accidentally in lab is not here, but there's a function or an argument you can add to paste called collapse. Normally, if you give a vector to paste, or let's say you give like 2 vectors, it will put those vectors together, but it will do it entry by entry. So if you gave it 2 vectors of length 10, it would put together the first element of this vector with the first element of this vector and paste them together. If you use collapse, everything you put into paste gets put together into a single string, a single element. It collapses all those individual observations into one continuous single string. This is an argument you do not want to accidentally use if you're collapsing if you're using a couple string variables in a data set with like millions of observations. It's going to create a single element, one string, that is millions of characters long, and it's going to break your R. It's going to get very upset with you due to the way this function basically has to put it together piece by piece and then allocate memory for it. Due to the storage limitations on single elements in R, it will get very upset with you very quickly. So if you use collapse here and you find your R locking up, you've probably just fed it an extremely long thing that it's now trying to figure out how to dump into a single cell in your table. Okay, so when we used functions on the reader package earlier, like read underscore CSV, read underscore TSV, all of those things, they have an argument called call types, and you give it a string of single characters that correspond to each column that say what those columns are going to be when you read those data in. In this case, if we gave loaded data in reader and we gave this argument, this would be saying column 1 is character, column 2 is character, column 3 is integer, column 3 is a date, or column 4 is a date, and so on and so forth, N for numeric, so on. So let's say you actually wanted to create a string of these column types from some data set you're already working with. So this is something, for instance, is if you want to export something or store something as CSVs, like you have to store it for CSVs for some reason, but you have specific column types you want for it that are already stored in your data, you could extract and create a string based on the data types that are there using these character commands we've used. So for example, we could use class to get the types of data, substring to get the first letter of the type of data, and that's what these are. So C is character, but character data is lowercase c character. Date is capital D. For reader, what it takes in are actually the first letter of the different data types that things are stored in as are. So if you get the class of each column and then extract the first letter of it, you're getting these things that go into the reader argument. Then if you paste them together with collapse, it would take all those individual vectors where each element of that vector is corresponding to a different column in the data set and put them together into one element. It'd be something like this. Let's say we have this restaurants data I'm working with. I say sapply restaurants class. This is running the class function on every column in the restaurants data and outputting originally a list simplified to whatever's the lowest level of data it can come out. It's going to pop out as a vector. Then I'm going to do column types is substring this vector here, 1, 1. So I'm grabbing from the first character to the first character. So I'm only getting the first character from each one of these values. And then I'm going to put them here and collapse. So it's going to take a vector where originally each entry in the vector was the actual name of the data type, like numeric, integer, date. It's going to slice off the first letter, collapse them all into one element. This would be if I take that restaurants data and just grab the first character of every class of every column in the data set. This is an argument you could feed straight into Reader to have it read in those column types for you. Don't know if it'd be the most useful thing in the world. Reader usually reads things in the right the first time, but say if you export it to CSV, it would lose all of its column types and want to load it back in. This would be a way to extract that. Then if you felt like it, you could create a function to do this for you. So typically I read in data using read CSV, and I don't even bother doing column types, but sometimes I know that like a new data set I'm going to load in has column types of a data set I already have loaded, like they're the same ones, and I've had to modify those column types manually. I could have something like a loop that would extract the column types from a previously loaded data set and automatically apply them to newly loaded in data sets using a function like this. This is that exact same code from the previous slide, but put into a new function called reader input types. You give it a data set, and it will output whatever column types are associated with whatever data frame you gave it. Let's say you had to modify some Excel sheet you're loading into your computer and assign data types manually to it for whatever reason, but then you needed to load in another 100 of those Excel sheets. On the very first one you load in and correct, you could extract its column types, and then in the loop that loads the rest of the files, you could just assign them to it and automatically load the column types. It's a little easier than doing it manually. I almost never do this, but I've had to do it a couple times. But it's an example of how you can put this stuff together into a function. Yeah. Okay. Paste 0 I've used in class a little bit. Paste 0 is just a shortcut to the paste function that sets the automatic separator in paste to be nothing, so no space between things. By default, if we do paste, so in this case I'm giving paste a vector of the integers 1 through 5 and then the first 5 lowercase letters of the alphabet. By default, if you paste, it's going to put a space between whatever is the item here and the item here. So I'm getting 1A, 2B, 3C with spaces in between. I could say paste separator equals nothing, and it will automatically remove that space. But if we're lazy and don't like even adding one extra argument to our paste command, paste 0 does the exact same thing. I end up using paste 0 a lot because I'm too lazy to fill in that argument there, and it saves me that like 5 characters of typing. All right. Okay. Good to know because I use paste 0 a lot, so if you see it in the code, that's what it's doing. Nothing fancy. Okay. So here's some examples of different outputs you would get for different use of arguments in paste. I'm not going to go through these individually, but it kind of gives you an idea of how different things operate in paste. So collapse isn't just a yes-no. Collapse, you can give it a character, and it will collapse, and in between the items that it collapses together, it will add whatever you put here, much the same way separate will do that. So if I do something like collapse equals exclamation point, it took those letters of the alphabet, scrunched them all together into a single element, and then put an exclamation point between them. Compare that to, say, something like separate equals plus here on paste without collapse. It keeps them as separate elements in the vector, but still puts that thing in between what it pastes together. So you might be able to think of reasons you want to collapse on things and add separators or be able to control that kind of stuff. There's a million reasons to do it, but mostly just know that this exists and you can do it. And this functionality will carry over into the other functions that I'm going to discuss here today. So, what I actually want to talk about today with regard to strings is a tidyverse package called Stringer. So, Stringer is another tidyverse package like those ggplot2, dplyr, tidyr, all those kind of packages we've been using up till now that focuses entirely on manipulating and doing things with strings in R. So Stringer is actually a wrapper for another package. So the functions that do all the stuff to strings today, we're going to be calling on them from Stringer, but what Stringer actually does is you give it arguments, and then it goes and uses a function in a package called stringy, which is really hard to use but really powerful. So it just converts what you want to do into some stringy command. I could teach you guys stringy, but its syntax sucks, and its command names are stupid, so we're not going to do that. Instead, we're going to use Stringer because it has elegant command names and nice defaults and easy to use functions. So we use Stringer. So what Stringer does is a few things. One thing it does is has equivalents that will replace those base string functions that I just showed you, like paste and endCharacter, with ones that have sort of uniform syntax and behavior. One thing they have is better error checking. Almost every tidyverse function has better error checking than base R stuff, which is nice. It'll add functions to do things like remove white space or add white space to things. And by white space, you could also be adding additional zeros to things. So if you want to say increase some character, you need to pad a bunch of zeros out to make an ID number of some kind. There's functions to do that. This is really common if I'm working with things like census tracts and I need to pad them out to create full census IDs that include the state, county, and city level information in them. Well, that's often separated by lots of zeros. There's functions that will just automatically fill those zeros in where you want them to without you having to go and manually paste stuff. There's also things you can do in Stringer or functions in Stringer that relate to pattern matching. That is, detecting, locating, extracting, matching, replacing things using regular expressions to describe the patterns you want to search for and replace. This stuff exists in base R and stringy, but they're a lot more confusing to use, and their names are often very strange. They're pretty uniform throughout Stringer, and these kinds of operations in searching through text to select things, delete things, add stuff can be really complicated. You don't want to make them any more complex than they already are, because I'm going to have to today teach you guys about how you use regular expressions, and you're probably going to be real happy I haven't made it any more complicated than I already have. One of the nicest things about Stringer is that every single function in Stringer that isn't a minor convenience function begins with str underscore. So if you want to do anything to strings and you can't remember what that function is named, in RStudio type str underscore and it will bring up, and then tab to bring up the autocomplete, and just scroll through the menu. Every function you're going to get is a Stringer function, and since they have intuitive names, you'll probably be able to figure out what it is you want to do. I find this to be really nice, and I wish more packages would do uniform names. Yeah. So, first of all, there's some basic function equivalencies between Stringer and base R stuff that we've seen. So, str underscore sub is basically the same as substring that I was talking about earlier, but it adds one really important piece of functionality that should make you use string sub over substring basically in all cases. It accepts negative indexing. So what normally with substring, let's say we wanted to get the characters, the last 3 characters of something, we would have to figure out how we can actually get that last character number by counting in positive numbers from the front. If every element of your character vector is a different length, this is kind of a pain in the ass. You have to use nchar for each of those and get it. In string sub, let's say you want to get the last 3 digits of something, you just say string sub -3 to -1. That will be the third from the end character to the end character. Negative indexing makes it really easy to grab things from the beginning or end of a string by counting either forward or backwards. This is great. So I basically always use string sub instead of substring for this reason. Never know when I'm going to need to negatively index. So for example, here I've done, okay, I want everything except the last 2 digits of Washington. So I've said I'm going to go from the first digit to the third from the end, so -3, and I get Washington. It works. Amazing. Another function, str_c, is string combine. Works just like paste, except its default is to have no space. So this one works like paste. You can give it a separator of your choice, but it defaults to having no separator. So it manages to replace both paste 0 and paste. So, string C here, by default, there's no spacing. So, I use this instead of paste when I remember it exists. Okay, other function equivalencies. str_length is equivalent to n character. It's a little longer to type, so I still usually end up typing n character because laziness. Works exactly the same. There's also some other functions in Stringer that are sort of like general before we get into the crazy stuff with regular expressions. There's functions for changing the case of things in your strings. So string to upper will change every character in a string you give it to uppercase. String to lower will change them all to lowercase. String to title will change them all to title case. It's often good to do these kinds of conversions, before you're going to search through stuff, because R is case sensitive. So if you're going to search through a whole bunch of text, and especially if the capitalization is uneven, or say you're searching through the text of a book or something, you want to swap it all to that same case so you don't have to like address uppercase, lowercase simultaneously while doing searches. So for example, in these data we're working with, the unique city names you could see include both lowercase and uppercase versions of Seattle and all these other ones. Well, I probably want this to be equivalent to that, but in R by default they are not. So I could just take this, change all of the character data or all of the like names, addresses, cities in the data, and make them all uppercase. And then if I got unique on them, then these two have been combined. Kent, Bellevue, Kenmore, Issaquah is no longer lowercase, so on. I tend to like working with entirely uppercase or entirely lowercase strings, so I'm not dealing with the kind of like oddities of trying to match case for everything, right? And you can always then swap it back later. That being like title case would put them back to look like this, or put them all back lower uppercase. It's always easy to convert back. Okay, so white space. When you load in text data in R from data sets that are not made for doing analysis or things like that, often people have inserted extra spaces all over the place. For instance, the very first observation I get when I get unique is at the shack LLC, and then there's a space after it here. Well, that space is just some artifact of however the data were loaded in or written in or something like that. You'll often get these spaces before or after things. There's a function in Stringer that will just remove extra white space. This is something that could potentially affect every single character column in a data set. So in this case, the very first thing I'm going to do is like, okay, let's figure out which columns are character data, grab those ones, and then apply a function to them to remove extra white space. So in this case, I've done something similar to what I did before. sapply restaurants class will generate a vector of all of the different classes. In other words, I'm looking for character vectors in here. Then what I'm going to do is I'm going to create a vector of the names of the columns that are character vectors. By doing this, I get names of the column types. Column types equals character. This outputs a vector of all of the names of the columns that were character data, which I could then run some apply function with string trim to clean them all up at the same time. As an example. So I'm going to take our restaurants data, I'm going to type it to mutate at. Mutate at is the mutate for doing multiple variables simultaneously, but not every single variable in the data set. It's almost no case you want to use mutate all instead of mutate at. The way mutate at works is it takes a argument that is the function vars, and inside that you can either put quoted or unquoted variable names. In this case, character columns is a vector of the names of the columns that are character data in our data set. So I'm selecting all of those columns. To those columns, I'm going to apply the function string trim. What string trim does, if you give it no additional arguments, it's just going to remove any extra spaces it sees at either the beginning or the end of any given entry in your character string. This is how you dump white space out of something. Okay? I've done string trim on every character column in the data set. You can see that one extra space we had here is gone. It's also gone from every other entry in every variable in the data set. If you want to do broad, like reshaping of your data, broad, like modification, say you want to convert every character column in your data set to uppercase, you could do the same thing that I just did, except instead of string trim, you could do lower to upper or whatever the hell, string to upper, string to lower would do it. Okay, now we're going to get into the fun stuff. I'm going to start talking about regular expressions and pattern matching. So, regular expressions are a sort of separate programming language that are basically universal across all applications. It's a logical language or logical syntax for telling a computer how to look for text, how to search for particular text patterns. The nice thing about regular expressions is everything I teach you about regular expressions is not unique to R. Every programming language that I'm aware of supports regular expressions, and it's exactly the same in every programming language that exists. It's a universal logical language for text searching, which is really nice. In fact, a lot of things that you probably use in the past have supported regular expressions without you even knowing it. All of your terminals on your computer, whether Mac or Windows, all support regular expression searching. You can make Google use regular expression searching, you name it. You can do just about anything. Your find function in most programs supports regular expressions. Regular expressions are how programmers are able to navigate and do stuff with text that most of us didn't even know was possible. They're very, very powerful. So, the way a regular expression works is we'll write some sort of expression, which is sort of a logical statement. We'll apply it to some sort of string, and then it will give us matches. We can do modifications to these matches. We could print those matches. We could just create a list of trues and falses for when those matches are detected. So, things that you could search for, or things that you can use in a regular expression, are literal characters, and those are the snippets of actual text you want to search for. Say we had a string that was all of the address information in this entire data set, and we wanted to search for SEA or maybe the number 206. You might say, I want to actually search for SEA, or I actually want to search for 206. We can search for that literally the way you just Google something, right? There's also meta characters in regular expressions that let us be flexible in how we describe patterns we see in the data. These things include backslashes, carets, dollar signs, periods, pipes, and a million other things. All of them have some sort of unique meaning in regular expressions that will control how it searches for stuff in text. If you want to treat a meta character as a literal character, that is, say you want to search for a period, you don't want to treat a period as being a symbol. Period by default stands for any character. If you want to actually search for periods, you have to do something called escaping it. And by escaping something in R, it means you put 2 backslashes in front of it, and it will search for that exact character. For instance, because parentheses are a special character in regular expressions that are used to indicate a series of things. If you want to search for actual parentheses, you'd have to do \\parenthesis. Then say we were looking for 206 in parentheses, we do \parenthesis, 206 \parenthesis. If you've ever attempted to put a backslash into a string variable or something in R and it suddenly yelled at you, it's because the backslash character in R is reserved for doing this. The backslash character in R is reserved for escaping special characters. This is actually something that's very common in a lot of environments, a lot of programming languages. Backslashes are a unique character. That's why it's really fucking annoying that Windows uses backslashes instead of // to do its directories. And that's why you cannot give a normal copy-pasted Windows directory as your working directory in R, because it thinks every one of those backslashes is escaping the next character in order. That's why you gotta change every single one of them. So Windows is stupid. Yeah. So, let's give some examples of how this works, because right now it's kind of abstract. Let's say we're looking at the names of businesses in this data set. Let's say we want to look at the data and we want to plot it, get some sort of idea of how filthy the average coffee shop is in Seattle. Well, we want to know which ones are coffee shops and which ones are not. We're going to make the assumption, at least I made the assumption here, that a coffee shop is anything that in its name, after it's been converted to uppercase, that in its name it contains coffee, espresso, or roaster. The regular expression for searching for coffee, espresso, or roaster is coffee, pipe, espresso, pipe, roaster. So this OR operator is kind of the same as the OR operator we've used in logical expressions in R. This is a meta character that means OR. Notice I didn't put a backslash in front of that because I'm not searching for the pipe itself. I'm actually using it in the regular expression, right? To search for things inside of character data in R using stringer, we will use the function string detect. So str detect. What it will do is it will return a logical vector that will be true when the string it's looking in contains whatever we gave it, that is the pattern, and a false if it does not see that in that particular string. So it's going to look once inside of each element of a character vector. If it sees coffee, espresso, or roaster, it's going to return a true. If not, it's going to be a false, and it's going to create a vector that corresponds to the length of whatever character vector we gave it. This is basically the same as the grepl command that I've used in lab a couple times. I think I've used in class. It's similar, but this one works a little bit better, so I should be using that instead of teaching people grepl in lab. So, how does this work? We're going to take our restaurant's data. We're going to say filter, string detect. We're going to look in the name variable, and then we're going to say coffee, espresso, roaster. That is, you give a vector, a character vector here in string detect as the first argument, a pattern as the second argument. We're going to filter down, and it's only going to include things that contain coffee, espresso, or roaster in their name. Well, I've done that. Now we see the sort of rows we're getting. So this is the names I've filtered down to. So they contain espresso, coffee, coffee, espresso, espresso, coffee. So, I mean, these are probably coffee shops or places you can at least buy coffee, right? So this is a way to subset then, rather than subsetting on like numerical values like we've been filtering before, how to search within relatively complicated text to look for some kind of keyword that we might want to filter our data set with. This is great if you're working with data that has a lot of text components. Yeah. Okay, so now I have a data frame that contains coffee shops. So maybe I'm interested to know if my coffee will kill me or not. So what I'm going to do is I'm going to take each unique business identifier, I'm going to keep its most recent food inspection score, and I'm going to look at a histogram of those scores. The code for that would be something like this, where I've taken this coffee data frame I've already filtered down. I'm going to select just its business ID, name, inspection score, the date, group them by the businesses, because the inspections work that they do repeated inspections at places, so every individual business could have between like 1 and 20 or 30 individual inspections. I only want the most recent one. I don't care if that coffee could have killed me in the past. I want to know if it's going to kill me now, right? So I'm going to filter so that the date is equal to the maximum date within that business ID. That is the most recent inspection for that given business. I'm going to say distinct, keep all true. So I'm going to, if there's any identical rows, I want them wiped for the given business. Then I'm just going to do a histogram of that inspection score. So most Seattle coffee shops have a relatively low inspection score. The inspection score is the number of violations that were detected during an inspection. Well, there's some coffee shops out there that are getting like 40 violations. It's a coffee shop. It probably doesn't even serve food, and it's getting 40 inspection things. That's the kind of thing where you filter it down, and you see where those are, and you do not go to those coffee shops, right? Next week, we're going to map these places, so that's a lot of fun. Get to see where they all are. What I like is a hint for next week, like one of the biggest, grossest violations in the data is actually a kitchen in one of the frat houses just off of campus. It's got like 75 violations in its last inspection. It's awesome. Anyway, so fun with data.
What does it mean by the width in the first line?
Yeah. So this is me mixing a combination of dplyr syntax and base R syntax. What the with command does is the first argument is a data set, and then its second argument is functions you want to run, and it will use the original data set to run those functions. So in this case, I'm doing with this entire dplyr chain is making one data frame, and then I'm going to run the histogram command using this data frame. Yeah. Ugly, but it works. is just to make it as compressed as possible. A better way to do it would be to get rid of the width, pipe it straight into histogram, and do $$ inspection score. Be the same thing. Yeah. Width is the base R way of doing it. I kind of slip back into using base R once in a while because I learned wrong because I taught myself. Okay, so looking for patterns with string detect. So let's say we want to look through phone numbers and we want to see all of the phone numbers that are in the 206 area code, 206 being the main area code for Seattle. Thing is these phone numbers in the data set, some of them contain 206 without parentheses and some contain 206 with parentheses. We want to get those 206s regardless of whether they have parentheses or not, but we don't want to get 206s that are, say, the middle 3 digits of the number. If we have a number like 555-206-1234, that's not the 206 area code. That's just this prefix 206. We don't want that. How can we come up with a regular expression that will get just phone numbers like these? So these ones have 206s in parentheses, 206s in parentheses followed by a space, 206s in here with no spaces. We want to get this, this, and this. We do not want to get that. The regular expression to do that would be something like this. Caret, backslash, backslash, parenthesis, question mark 206. I'm going to disassemble this to show you guys what's going on. If we run that, it's going to say true, 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 false. So it's getting what we want, right? But how the hell does that thing work? So, part by part, caret is a meta character that anchors you to the front of the string. It's called the front anchor. This says, okay, the regular expression, whatever I'm searching for, can only occur at the beginning of the string. So I put caret here to say, okay, the beginning of the string has to be here. Whatever follows this caret is going to have to be the first character in the string. Okay? So I've anchored it to the front. This is to avoid getting a 206 that's in the middle of a string. Next, backslash, backslash, parenthesis, question mark means I would like to look for a left parenthesis, backslash, backslash, parenthesis, this backslash escapes, this backslash escapes that parenthesis. It's stupid. But that's the way you gotta do it. Double backslash, that. So we're looking for an actual parenthesis, not a meta character parenthesis. But then the question mark tells it that whatever this is that precedes the question mark is optional. If it's there, include it. If it's not, it doesn't have to be there. So we're allowing a parenthesis to be the first character, but it doesn't necessarily have to be. Next, 206 is the literal character we want to find. So after an optional parenthesis, we want to look for 206. So the string is saying, at the beginning of a string, there can or can't be a parenthesis. I'm okay with either of these, but the next thing I need is a 206. Return that whenever that's true, or return a true whenever it finds that, and a false otherwise. So we get this. That's going to fulfill that condition. There's no parenthesis, but it's optional. The 206 is at the start of the string. We get that. Here, there is an optional parenthesis. Then there's a 206. That's a true. Parenthesis 206, it's true. This 206 is in here. It's not anchored to the front of the string, so it returns a false. It's the power of regular expressions, right? We're parsing out something relatively complicated and getting what we want. Does that make sense to everybody?
What's the fastest way, so once you have like a logical vector, what's the fastest way to then get the rows that each one represents? So through indexing, or would you like to
So do you just want those ones, like filter them?
Yeah.
You could put this straight into a filter. So the nice thing about filter and dplyr is filter actually filters by logical vectors, because all the statements you run in inside a filter, like if you do something equals equals, that's actually returning a logical vector, and so it just cares about the locations of the trues and falses. So if you just put, string detect, whatever variable you want to sort by in the pattern, you put that straight in filter, no additional statements, it'll filter to those rows. So I actually did that for, that's what I did here. See, with the restaurants, filter, string detect, the name variable, and the pattern, that's it. And it'll subset to those data. So string detect and like that is actually really great for filtering. It's super easy to use. You don't have to add any additional things. You don't have to do equals equals true, any of that kind of crap. There are other stringer functions that I'll talk about at the end very briefly that instead of returning a logical vector will return the actual values found, or the numerical index of the values found. So you can get a logical vector, numerical values, or actual values using different functions. I'll mention them at the end. Yeah, Stringer's got something for everything. It's pretty great. Okay. Stringer also has a function called string view that opens a viewer pane that will show you exactly what text is being selected in your data. It will actually bring up, it'll render a web page and highlight the things that the pattern you give will highlight. So let's say you're working with a bunch of text data and you just want to know whether you're highlighting the correct stuff. You could do string view, say those phone test examples we did in 206, it'll bring up a web page showing all of the values that are in that actual vector, so the whole vector of data, but it will highlight the ones that your string detect returned a true for. This is sort of a quick way of testing your regular expressions, like if you need to iteratively do a complex regular expression on actual data. One thing, though, to be careful is that because this is actually rendering a web page in your viewer window, don't load like a 10 million line vector into that, because it has to render that web page before it can display, and it will destroy your R if it tries to load something that large, because it's actually making an HTML page. It just annihilates your memory. So be careful. I like to get like, do like head 50 or something like that, get like the first 50 observations, and then run a string view, and it'll pop it up. An equivalent to this that I have on the web page, let's see, that might be useful to people. There is a website here for regular expression testing. So what this does is that allows you to write like a regular expression up at the top, and it will highlight in here all the text that would be selected by using that regular expression. And then it has like a built-in cheat sheet and examples and like a reference guide over here that you can browse to figure out, like, okay, how do I anchor to the end of a word? Oh, $. Has some information on it, and it shows an example of how it's used. So this website, which is just regxr.com, lets you kind of figure out how to put regex together in a sort of what you see is what you get environment. Pretty cool. One thing to remember, though, is that in R, each individual element is usually a single string, whereas in this particular site, like this entire thing is one string. So it works a little bit differently if you want to search within many, many strings individually versus you want to get like multiple repeating things inside one incredibly long string. I recommend toying with it to figure it out. But regex is something where you're basically learning a new logical language. Much like learning with R, you kind of got to mess with it before you get a real good feel for it. I'm going to try and give you guys a base, though. Okay. Yeah. Okay. So maybe we want to know something like how many rows in our data set have non-206 numbers. So which ones have area codes that are not Seattle's normal area code. Might do something like this. Take our restaurants data, make a new variable that just has 206 number with that string detect, phone number, area code 206 pattern, right? This is going to create a logical vector that is true or false. True if there's a 206 number, false otherwise. I'm going to group them by whether they have a 206 number or not, and then tally them. So this is going to create essentially a crosstab. So we see only about 67,000 numbers do not have a 206 number, about 110,000 do, and presumably about 83,000 don't have a listed phone number because they got an NA. Can't search in something that doesn't exist. Oh. So, if we're doing something like, string detect those true falses, you could use them in something other than a filter. If you just want to do tabulations or grouping by, whatever. Use them for other stuff. Just like creating any other variable. Okay, so let's say we want to extract some data rather than just get trues and falses for something. So what I want to do here is I want to extract from the address data here the directional part of the address. So if you're not familiar with the layout of Seattle, Seattle actually in its street naming has a really elegant layout with regard to what they refer to as their directionals. If you go on streets, you recognize that there's something like, 65th Northeast or something like that. There's a very specific quadrant of the city associated with every single one of these that is completely uniform. If somebody tells you a street is, say, something northwest, you will know exactly where in the city that is. Because, I'm actually going to bring it up as an example. This map right here are all the quadrants in Seattle that are defined by directionals. It's this downtown area projected in each direction, cardinal direction. Every south street in Seattle is in this block. Every southwest is in this block. Every west is here, northwest, northeast, north, so on and so forth. Right? So that means you know what region of the city it's in just by extracting that directional from it. And this is why I'm doing what I'm doing. Okay, so let's say we want to extract that. So what I'm going to do is I'm going to use this pattern to search for things. This is where we're going to use those parentheses, and this is why they're used as meta characters. So what I'm going to look for in a pattern is I want a space. The reason for that is because the directional should be isolated from the rest of the string, and it never is the first thing to occur in an address name. So space. Then what I want is any one of these directionals, north, northwest, northeast, south, southwest, southeast, west, east, one of them. So these parentheses are containing that or expression, saying at least one of those things, but any one of those things, followed by either a space or $sign. $sign is the meta character signifying the end of the string. So it's okay if these things are followed by a space and then some other information, but it's not okay if these things are butted up against some other text. I don't want something like, the W to be the first word or the first letter of the street name or something like that. So these need to be isolated or occur at the end of the string. So if we had some kind of test data, let's say we had addresses like this, 2812 Thorndike Avenue West, 512 Northwest 65th Street, 407 Cedar Street, 15 Nickerson Street. We want to extract the directionals. You see two of these don't have a directional at all. These two have a directional. One of these has a directional nested inside of that. We want to extract out only those directionals. If I run this pattern here, I get west from Thorndike Avenue West, northwest from here, and NAs for these because nothing was found. So the way this works, as I kind of described, the first space in our pattern matches a space character. So in this case, like the Thorndike Avenue West one, it's matching this space here. It would also match this space here, but that space then has to be followed by one of these directionals, and it isn't there, so it's just going to match it there. This matches any one of the directions in the group, just one. There should only be one in any given address. And then that is a group saying that there's either a space after it or it's the end of the address. So the caret anchors the beginning of a string, $sign anchors the end of a string. If you want to search for either a caret or $sign literally, 2 backslashes in front of it will let you search for it literally. Does that make sense to everybody? This one's not too crazy. I'm going to get a little nuts here in a minute. Okay, so let's say where in the city are all the addresses in our data? Well, we have those directionals, so we can get a general idea of the region associated with where all these restaurants are. Right? So what I'm going to do here, I'm going to take restaurants. I'm going to reduce the data set to the distinct addresses so we don't have duplicates, because by default there's multiple observations for each restaurant. I'm going to mutate a new variable called city region, which is the output of that string extract, but trimmed to remove that extra white space, thus the string trim thing I mentioned at the start. Group by the city region, tally and arrange descending. So I'm creating essentially just a tabulation of all these regions. We see that the dominant area for restaurants in these data is the northeast region of Seattle, followed by the south region, followed by NA. NA is the city center because there's no directional associated with it. Or, if there's no address, we'd also end up with an NA, but all the addresses are at least in this data set. Then north, southeast, southwest, east, northwest, and west. Right? So, these regions are unevenly sized, so part of it is that the northeast region is really, really quite large, and the south region is also really quite large, but now we know where most of the restaurants are. Okay? Another thing you might want to do is finding text, some particular portion of text, and then replacing it with some other value. To do that, we can use the function string replace. So let's say we want to do in this case, a street level analysis of inspections, that is comparing things like University Ave to Pike Street. But because the addresses have building numbers in them, we want to remove all of the building numbers and just get the street. So essentially what we're doing is we're finding text and we're replacing it in this case with blank. But you could just as easily as we do this here, replace it with other text. So what we're going to do is there's going to be a pattern we're going to use to get address numbers to remove them. This is the regular expression I use to do that, which I'll decipher here in a second. It's a bit of a nightmare. What we're going to do is run some test examples. So these examples kind of cover the gamut of potential addresses you could encounter. You could see something that's a pretty straightforward one, like 2812 Thorndike Avenue West. That's pretty easy. We just want to get rid of the number. Let's say we just had First Avenue, nothing. We just want that to stay the same. But then if we had something like 10A First Avenue, 10-A First Avenue, 5201-B, or this sometimes happens in Seattle addresses, 7040 and a half 15th Avenue. We want to get rid of all of those numbers, unit numbers, everything at the beginning of them. All right? This expression will do it. This is going to be the output. Let's break down how that works. So, caret bracket 0 through 9 means look for a digit between 0 and 9 at the beginning of it, at the beginning of the string. Asterisks means match multiple ones. So that will look for any number of digits in a row. So long as they are numeric digits in a row, it will match any number of them at the beginning of the string. Dash question mark means, okay, there could be a hyphen, but it's not necessary for there to be a hyphen. Then bracket A to Z means optionally match a letter, only one letter, but optionally there may be a letter. Then match a space. Then if there's a 1/2 followed by a space, match that too, because it turns out there were a bunch of 1/2. So this is sort of a special case thing. Now, does that make sense, what's going on here? Any questions about that? There's a lot of operations going on at
Why would
once.
the question mark be after the parentheses rather than after 1/2?
Because we're saying that this entire thing, if the question mark was there, it would be,
Oh, it would leave the space.
it'd be, well, yeah, it'd be the space would be optional. So we're saying that this entire statement here is optional. So in this particular case, like, because the question mark follows the dash, it's saying only the dash is optional, but not like the asterisk and the stuff before it. And in this case, like, this is saying the entire brick here. So these sort of, both brackets and parentheses are refer to groups or groupings of things. Any sort of modifier you put on the outside of the group will modify the entire contents of that group. Yeah. Yeah. That's mostly a thing for parentheses, because parentheses are used to put a whole bunch of things into a group. Parentheses do nothing else in regular expressions than group things together, just so that we can use this like optional operator. Anything else? Okay, yeah. So, in this case, ran that regular expression. For the first one, we dropped the number. Nothing was dropped for First Avenue. The reason for that is because we searched for a number followed by a single character. Well, this is followed by 2 characters, so it didn't drop it. So it kept First Avenue here. First Avenue is the same there too, because we dropped 10A. We dropped 10-A from this one. 5201B was dropped here. 7040 and a half were dropped from that. So we've extracted the streets and kept their directionals and everything. So might be how this string would, to most data sets with addresses, would pretty much do the job in most cases. It'd be a little more complicated if, there was some cases where like first streets were actually listed as 1S or something like that. If you had some weird truncated data set, you have to figure out cleverer ways. The easiest way to do that would be to replace all of those with like 1ST or something like that. You'll have to figure out tricks for working with particular text data. Okay, so now what we want to do is we want to replace those street numbers, and what we want to replace them with is nothing. So what we're going to do is we're going to take our restaurant's data, mutate, It's going to street only variable is just going to be our address variable with the street numbers replaced. So we're going to go street only equals string replace the address variable, address number pattern. So this you give it the pattern here for what to search for, and then a replacement. The things that exactly match this pattern will be replaced with whatever you provide as a replacement. All right? So it just did that. This is exactly what we showed in the previous one. So this is a way to create a variable that has dropped that additional information that we've selected. You could conceivably search and then replace it with something else. So if you actually had something rather than drop it, you want to replace it with some actual value, you could just put that in the replacement. There's another function called not just string replace, but string replace all that gets a little more flexible, where you could specify like a given expression and one replacement, and then a different expression and a different replacement, and simultaneously do multiple things. String replace all is pretty flexible. It also lets you do things like the first match gets replaced with one thing, the second match in the same string gets replaced with a different thing. It's like combined things. Yeah, it gets pretty nuts. But yeah, so string replace all.
Shouldn't that have been streets at the beginning of that function?
Streets?
Or, I mean, street only. I'm just, because you have restaurants equal to restaurants.
Yeah, I'm replacing in the restaurant's data. I'm replacing it with a new data frame with an added column, street only.
Oh, got it. Okay.
Yeah.
Got it. Okay.
Okay. Cool. Now, here's something even trickier. So we looked in these data over here, and some of these have things like unit 1700A, number 125, building C08. Well, we want the street. We don't also want these like unit numbers or something added to the end. So let's see if we can get rid of the units and the suites too. So getting rid of those things is tricky because there's a huge variety in what those things could be. But what I'm going to call a decent attempt to remove them would be to drop any text, including an after a pound sign, so a number sign, suite, shop, or unit. In this case, this building one, so if this is, like if that's Northwest Gilman Boulevard maybe, but C08, that might not get dropped by this particular syntax, so you'd have to tighten it up to really get everything, but it's kind of hard to get everything. You have to look for all your special cases. Might do something like this. We have this address unit pattern we're going to create. It's going to look like this, which I'm going to describe again how that works. We can see that it gets rid of pretty much all of these issues. So for something like Rainier Avenue South, number A, what the fuck does number A mean? It would remove that. For Fauntleroy Way, Southwest Suite 108, it would just reduce it to Fauntleroy Way. So it appears to be getting rid of at least these example cases. Works? So, how does that work? This is what that syntax looks like. It looks pretty similar to like the second or third example we did. So, first thing I'll do is match a space. So, any one of these things needs to be occurring in isolation, so after whatever other text it begins with, and not occurring in the beginning of the string by, there's no white space at the beginning, so it doesn't occur at the start. We're going to match pound sign, suite, shop, unit, one of those words, followed by any characters at all. Period is any single character, no matter what it is. Period plus asterisk is any characters at all in perpetuity, just forever out from that point. It'll select everything following any of this. Yeah, so basically what this is going to do is it's going to select something like a $sign and then everything that follows a $sign to the end of the string, which we're just going to delete. We're going to assume we don't care about anything that occurs after any of those things. Yeah.
Is the suite or the character is case sensitive?
Mm-hmm. So these are all, the searches are going to be case sensitive, which is why I've already converted them all to uppercase. So it gets a little more complicated if you have a mix of upper and lowercase. If stuff is uniform, you don't have to convert it first. But in this case, because it was completely non-uniform, I converted them all to uppercase just because it's easier to deal with. You can always convert them back later if you want to. All uppercases I find to be quite readable anyway, so I'm perfectly happy if all my data is in uppercase. It's very readable. All lowercase for some reason bothers me, and I don't know why, but it does. Yeah. Cool. So now let's remove units and suites in the data. Same operation as before. We're going to take that street-only variable that I'd kind of created before. I'm going to do a string trim on the outside of it, so because there might be some leftover white space from deleting these things, I want to make sure to get rid of that white space. Inside of that, I'm going to do a string replace on the street-only variable using that address unit pattern. Replacement is nothing. And now we get, for the most part, isolated addresses. Get things like Southwest Avalon Way, First Avenue, Northeast Bothell Way. We get this one that's now going to drive me insane. I have to figure out a way to get rid of it. Northwest Guild Boulevard, C08. When I first made this one up, that was not in there, but these data are newer than the data was before. So now I know about that. And next term, I'll get you building or whatever, C08. Yeah. So, pretty complex operations, multiple operations on your strings, but it's a tractable problem. You know, this is something that would be very difficult to do if you didn't know regular expressions. By difficult, I mean essentially impossible to do without regular expressions. Cool. So, now we might want to know something like which streets had the most restaurants with scores above 45. That is, what streets are most likely to poison me? So, what we want then is we want to get a data set with one row per restaurant, per date with the score, and see which ones above, which streets, places above 45 are on. So I've kind of put some dense code right here. This is just selecting the variables I want, getting distinct cases, filtering down to those with inspection scores over 45, grouping them by the street, and tallying them. So we see the streets most likely to poison you are University Way Northeast, South Jackson Street, Pacific Highway South. So everyone know where South Jackson Street is? In National District. Pacific Highway South is Aurora, right? Northeast 24th Street is, yeah, it's like the, what do I call that? It's the sort of the area, 24th going up like Capitol Hill area, a lot of restaurants, and Rainier in the south. So it's basically places that have a lot of restaurants, but it's like a lot of small restaurants and like small places. And basically, almost all of my favorite places to eat are probably in this list. In fact, many of them probably have those health violations because I really like dim sum. But it's just good to know. Next week, we're going to map these things so you can actually see where they're at, which will be kind of fun. Yeah. So, another operation you might want to do is splitting up strings into multiple columns, right? Because often you'll get strings that contain, you know, a lot of different information in one go. Common is getting people's names in like first and last name. You want to split those into separate columns. Or say getting an entire street address that includes the city and state and everything, you want to split it up into components, right? You could do this with tidier separate function, which is actually quite similar to this, but you could use string split, which I think has slightly nicer syntax and is very specific to operating on strings. So what string split does is you will give it some sort of pattern that defines where you want to divide the string into multiple variables, and then it will put the output from this into a list. The reason it does it in a list is because you might have, so let's say that you have something like, you know, let's say you have some data where like the first observation is this, the second observation is this, and for whatever reason you want to break out every character into its own column. It has to be a list because this is going to produce two columns. We'd be producing a column C and a column 2. This would be producing 3, right? So this one, if you were in a matrix, this one would end up having to be NA. If you do it in a list, it doesn't care. These can be different lengths. So by default, it does it in a list. If you're splitting up something that will always be split into, like every single item will always be split into the same number of things, you can use a version of this called string split fixed that outputs a matrix instead of a list. So basically, if you have stuff like first name, last name data, you might use string split fixed if you know every person in the data set has a first name and a last name properly spaced or something like that. Otherwise, in that like empty area, it will put NAs wherever there's no data. Anyway, so string split will fix that. How does it work? String split fixed here, I'm going to call the restaurant's violation description. All of these things are set up in a way that they have some violation number, space, dash, space, and the text that describes that violation, right? So what I'm going to do is I want to split that up into two columns. One is the number of the violation, and the second column is the actual text describing that violation, because maybe I'm more interested in the text, I don't care about the number to begin with. String split fixed here says I want to split these data by this separator always into two columns, or two values. So what I've done is I've created a list here. This is, so the violations numbers are going to be whatever preceded that space dash space. The second element of the list is going to be the vector of all of the things on the right side of that separator. So in this case, like violation 4300 is associated with non-food contact surfaces maintained and clean. So if somebody had this violation 4300, it would mean that their non-food contact surfaces were not maintained and clean. Okay. So if you're interested in seeing the actual violations that your favorite restaurants got in the data set, you can break them out like this. Nice. Yeah. Does that make sense how that works? It's good to toy with these different string split ones. Yeah. Okay. Some other useful stringer functions you might want to know about. I mentioned this. String pad, given a string, a width you want the output to be, a side to add padding to, and some value you want that padding to be, it will pad out any string so that every string in that vector is the same width. Right? This is great if, say, like something I talked about was I have lots of census stuff. Recent thing around here. So census IDs will typically, like in Seattle, look something like 530.00.11400, where this is the like tract ID, this is the like county ID. It looks something like that. Well, maybe what I actually want is just this tract component, because down here this is just made for if they subdivide a census tract, it gets divided into 0.01 and 0.02. If they divide them again, it goes 0.02, 0.01, 0.02, 0.03, so on. I often don't care about that. If I wanted to extract this and use it in my data, I could. But then if I have to put it together into an ID, what I have to do is make sure that this component, the full tract, is at least 5 wide, and then I need to tack on zeros here, you know, in 5300 or whatever, make sure this whole thing is the same width. I'd use string pad and different operations to sort of fill this out. It's kind of handy. If you work a lot with things with numeric IDs that you manipulate, string pad's pretty handy. Another thing, string subset. Given a string and a pattern, this will return the actual elements that contain matches. So before we use string detect, which returns a logical vector, this will return a vector of the actual matches themselves. So instead of trues and falses, you get whatever those matches really were, the actual values. String which works like string detect, but instead of returning a true-false logical vector, it will return the numeric indices of those elements. So instead of saying, like, if you have a vector of length 100 and giving you 100 trues and falses, instead, let's say that your detect only matched with like elements 35 and 46, it would just return a vector of the numbers 34 and 46, right? Numeric indices. Basically, this is good for subsetting stuff in particular ways inside of functions and things like that if you don't want to do the whole logical vector. And then the other one I mentioned was string replace all, which will do multiple replacements and sometimes complicated combinations of replacements, replacing things like in order, giving different values depending on their position. It does a lot of weird stuff. It's kind of hard to explain. Yeah. So, that's all I have on strings today. It's a short class. So the people who didn't show up got to not enjoy this extra short class for today. It's terrible people. So anyway, coming up, homework 6. What I assigned last week, it's due next week. Peer reviews will be due the week after. As I mentioned before, we have 11 weeks of class, which I've never had before. And so as a result, I only have 10 lectures. So the question is, to the people who actually showed up, to the people on the camera, I don't care about your opinions because you're not here. To the people who actually showed up, what do we want to cover in week 11? In my email earlier, I presented a couple ideas. So those ideas I had were doing something like tidy model output, that'd be creating nice regression tables and visualizations of regression output given some sort of models. So in this class, I assume no statistical background for anybody, and thus I tend to like go past that, but sometimes that's a huge pain for people. So having an optional day on it, I'm perfectly happy to go over that kind of stuff. It's probably useful to people. Another option is looking at advanced or applied data manipulation. That'd be things like doing complex variable creation, that is like creating variables that are based on many other variables, complicated like if-then statements, general data reshaping, like how do you do entire data sets from long to wide and things like that, and good practices for data creation, like if you generate variables, how do you create other variables that tell you why you generate them that way, like flag variables, descriptive type stuff. In other words, good data husbandry. Yeah, so those are two ideas I had that are things I thought about having lectures on in the past, but I'm wide open to any other suggestions on anything people want to do. I can at least give a wing at it. You know, I can't guarantee I'll know how to do it, but you know, maybe I will. So, opinions?
If we did the tidy model output, how adaptable would that stuff be to things besides regression? Like if we focused on regression for that class, would we be able to take that code and like pretty easily modify it to do other sorts
What
of
other stuff would you want to do?
outputs? Structural equation modeling.
Yeah, well, I would consider that all under the framework of
okay.
regression. Yeah, well, structural equation modeling is kind of unique in its in how you want to display stuff, because typically for that you want to display a whole path diagram. And the way I would usually do path diagrams in structural equation modeling is, well, actually, there's two different things you could do. I think the Lavon package for structural equation modeling can do some limited visualizations, but normally what I would do is I'd actually recommend learning LaTeX to make really nice path diagrams. That's how I do all my structural equation model output. I display as really pretty path diagrams with all the coefficients in place. Yeah, that's a little complex thing. There are packages that do it in R already using rGraphviz. And that's a little specific. But you can learn rGraphviz, as a side note, if you take the categorical data class by Adrian Dobre. It actually has rGraphviz covered in it a little bit for log linear models, and that stuff will actually carry over, and Lavon can output stuff to rGraphviz to do that. Yeah, that one I wouldn't cover for that, just because that's kind of a special case. It's a little different from other things. Normally people are interested in things like plots of marginal effects with confidence intervals and stuff like that. For people who have taken MLE or in MLE, a lot of that revolves around doing that, except with packages that have really weird syntax that I don't like. But yeah, so there's nicer ways to do that. And that would be using, there's a package called Broom, which is a tidyverse package that sweeps models into data frames. And that's really cool. So it would take like all those list output from like an LM, but anything. It'll work with GLM, it'll work with any dang model, period, and it will sweep it into a data frame that's plottable in ggplot using the exact same stuff we learned. Really handy, yeah.
You were thinking about going over?
That's why I was going to teach Broom. To write this lecture, I will have to learn to use Broom, because I myself have not used it. Because I'm doing things the bad way right now. So it's actually beneficial to me to learn how to do that. I'm like, oh, this is great. I can learn Broom finally, because I've been putting it off for like a year. Whereas the flip side of that is this advanced and applied data manipulation, where I would actually be teaching this stuff I basically do every single day and hate myself for, which is cleaning really complex, ugly data sets that I don't know where they came from. Like, I don't know how the data were collected and look like that. But this is like, my life is spent doing this, so this makes me unhappy, but I'm good at it. This I don't know much about and makes me happier. So, but I'm also willing to do both. So if we wanted to do like some of this and some of that, I'd be happy to do both too. And also, any other suggestions, I'm wide open if you guys got ideas. So it's the stuff you guys are working on, that kind of thing, like problems you're running into. Yeah. So.
I would vote for model output just because it's useful. That's just me.
Yeah.
Yeah.
Model, or like both.
I shouldn't have said
I
anything.
would say prioritize
Model output?
but if you have if you
No. I might at least delve into a philosophical discussion about this because I have some very strong opinions about how data cleaning should be done that they don't teach anywhere except through accumulated experience, which is an abomination that does a disservice to every person who goes to grad school.
So is that we're going through like your process?
That'd be part of going through my process, but it would also be actually showing real code examples of the process too. So it's like, this is how I do these things, this is why I do them, this is why they look more detailed and complex than you think it should be to do this stuff, because it's kind of like, it kind of delves into the discussion of the 9 circles of data hell, like how you get into these data sets that are just horrific, and because they are horrific, you have to build in so many checks constantly in everything you do, because things will be bad and wrong, and they'll be bad and wrongs in ways you probably couldn't even conceive of, so your shit needs to be bulletproof when you do stuff. And any decisions you make in the process should be documented, preferably documented internally in the data set. So, yeah, I have a strong philosophy on that was beaten into me with sticks by many demographers over the last 4 years. So,
that'd be helpful too.
yeah, so I can go into that. I'll probably, okay, I'll do both.
I also want to see when you choose the model,
Mhm.
when you do the regression, whatever you estimate.
Yeah.
So you have to choose what should be on the table, right?
Yeah.
I just want to see how I can compare which model is better or not. So that kind of process, not only for the final stage of the
Mhm.
output, but I also wanted to see the process.
Yeah. Well, some of that, and I could talk about some of that. I should talk about briefly right now. So, often deciding what models to use is often
Or variables.
yeah, variable selection is, there's a science to it, and there's also an art to it, and there's a philosophy to it. So there's different people in different disciplines will argue with each other very vigorously over how variable selection should be done. If you're in a discipline like sociology, most people say you should come in with an idea of what you want to use and generally stick to that. If you're dropping things that would normally be important, you got to justify dropping them. If you're adding things that normally seem nonsensical, you should justify that too. There's also machine learning sides where they're like, it's kind of a black box. Let's throw everything out, see what sticks, but be very aggressive about dropping things. So that's things like adding every variable you can, but dropping ones that don't cross some threshold on like a Bayesian information criterion or something like that. Different ways to do it. That's philosophical. As far as what to display and what to show, I believe you show everything humanly possible to show, but do it in a way that isn't confusing. And generally, regression tables benefit almost no one. A regression table is something that should be in your appendix, not in the main body of a document. So I will do really nice regression tables and send them in with the full expectation that they will not be in the body of a paper, and instead some very coherent tight graph that shows everything needs to be is there, and then the documentation being like, okay, if you want to see the table, go into the appendix. Some people are really going to want to see the table and want to see the coefficients, but they're about 1 in 10 for people reading your paper who actually want to see tables. Those huge regression tables that are always in papers, I don't even usually look at those things in detail. I glance a couple things. If I don't trust their numbers, I go back and check them. But they're usually just this big monolithic thing. And that's even for somebody who's I read those things like I read text. They're perfectly comfortable no matter what the models are. I still hate them. I don't like looking at that shit. I'd rather them just display them nicely. So something like this is going to be yes, how do we create nice, pretty tables with LaTeX or Markdown output? But how do we visualize too? And if I can, it'd be also stuff about simulating confidence intervals and stuff like that, bootstrapping errors and things, if I can sneak that in there. Because if you want to do nice confidence intervals, you don't want to assume that your confidence intervals are uniform across the entire range of things. You want to at least loosen them up with some micro-simulation. But yeah, MLE is great for that. I just don't like the packages they use in MLE, so it's like taking the philosophy in the MLE class, but applying it to packages that make sense. Well, that's it. If you have other ideas, email me. Especially, and also even if it's just, even if it's ideas that fit within these things, if there's anything that fits within them especially, shoot me an email. I'd love to see it. Because I'm kind of going in blind with these. It's not a lot of time to write a new lecture. So I'll figure it out. Yeah. Cool. Thanks for showing up. You responsible people, you.